All right, physics of energy. Again, all introductory stuff right now. So, what do we know about energy? Okay. Um, well, simple question, maybe difficult to answer though. What is energy? So energy is E equals mc squared. So energy is mass, right? Or mass is energy. Okay. Um, but okay, someone else. Well, what's energy to you? What can you do with energy? You can move things. Okay. In fact, I think that probably is one of the best definitions of energy. Okay. Um, Simply put, energy is the ability to change the motion or state of an object. Okay? Said in another way, energy is the ability to do work. Okay? If I want to pick my coffee mug up off the table, can I pick that coffee mug up without using any energy? No. I had to grab the coffee mug, contracting some muscles, and I had to pull against gravity, right? Even if we were floating around on the space station, okay, you guys ever seen the videos of the astronauts up on the space station, right? Everything's sort of floaty, right? Because they're in microgravity. There is no gravity pulling things down. There is no up and down in outer space, okay? But this coffee cup in space still has mass. It would still take some energy to change the position or state of this coffee cup, okay? I can lift it up, can move it around. That all took energy, okay? The state of this coffee cup right now, what does it look like to you? Are all its particles pretty much organized? Yeah. But what if I dropped it from a height? It'll break, right? Well, what is breaking? Breaking is changing the state of the object. All its pieces are put together right now, all its particles are connected, right? If I drop it, what am I doing? I'm releasing energy, right? In order to drop it, I had to have. So if I left it here on the table, is it going to do anything on its own? No, pretty much no, right? We have pretty good evidence that coffee cups left alone on tables don't spontaneously blow up. Okay? We have pretty good evidence that coffee cups left on tables don't spontaneously jump off the tables, right? Unless you have a cat, in which case it'll put some energy into it and knock it off the table, right? So in order to get this coffee cup to fall, I have to pick it up, okay? And I have to move it, right? That's putting energy into the cup. I'm taking it, I'm lifting it. I'm putting, we'll cover this more in a moment, I'm putting potential energy into the cup, energy of its position, okay? Then I let it go, okay? When I let it go, I'm converting its potential energy into kinetic energy, okay? And as it falls, it gains kinetic energy and loses potential energy. And when it hits the ground, its kinetic energy is put into the ground, but Isaac Newton also told us that any action has an equal and opposite reaction. So the cup is hitting the ground, but guess what? The ground is also hitting the cup. Okay? So then that energy is deposited back into the cup, and this cup is not made of rubber, it's made of, porcelain or whatever cups are made of, right? Cup material, okay, brittle. And when enough energy is put in it, because if I don't want to splash anything, but if I drop my cup like that, right, it didn't blow up, right? But I still dropped it. I still take it from a height, and I dropped it. Didn't blow up, okay? I put potential energy into it, and I converted it into kinetic, and then it hit the table, okay? The table hit back at the cup, but the cup didn't blow up. The cup didn't shatter, okay? However, if I go from a high enough height, and I put enough potential energy into the cup, and then I let the cup go, it will acquire on its way down, convert on its way down into kinetic energy, and that kinetic energy will be fed back into the cup when the cup hits the ground, and it will overwhelm the chemical bond between the atoms and molecules in this cup, okay? And those atoms and molecules will separate. I'll put kinetic energy into the atoms and molecules, and they'll separate. In other words, the cup will shatter, okay? Yeah.
So how come, let's say the cup was rubber and it didn't break? Or what's this like?
Yeah, so when you drop the cup, right? If the cup was rubber, well, let me say it like this. If I drop the cup from here and drop it to the ground, it does what? As we just explained. No, regular cup.
Oh, regular cup.
Shatters, right? Okay. You took potential of having the cup in the air, you converted it to kinetic energy, and then you hit the ground, you turn that kinetic energy back into the kinetic energy of all the particles in here, right? And it shatters. All those particles go in opposite directions, and cup pieces go everywhere, right? But if the cup is made of rubber, rubber has the property that it can spread out the kinetic energy deposited into it through all of the molecules, and all of those molecules can all move a little bit. Okay, and so if the cup is rubber, what happens to the cup? Let's say it's not a cup anymore. Let's say it's a ball, a rubber ball. Okay, what happens to that ball when I hold it from here and drop it? Hits the ground, and then it bounces, right? It bounces off the ground. Well, that is the kinetic energy from the impact at the ground being fed back into the ball, and instead of the ball ripping apart, that kinetic energy is expressed as the ball bouncing. The rubber ball is able to store the kinetic energy and then put it back into its own motion, okay? Where the cup can't do that. The cup's particles are just overloaded with energy and they break apart, okay? So energy is not a thing. Okay, it's not like I can take a ball of energy and give you this ball of energy and you can do something with it, right? Energy is not a thing. Energy is what we think of as, and it even says it right here, energy is a conserved quantity. Energy is the thing that entered the equation and will be the same on the other side of the equation once we're done with any calculation. Energy is conserved. It's just a quantity. Energy is not a specific thing. Energy takes different forms and can convert into different forms, okay? But energy is not a thing itself. It's just the ability to do work, to change the motion or state of an object. And the more energy you have, the more work you're able to do, okay? So there's a base unit, like a fundamental unit for energy, and we call that the joule. What's nice about the joule is that the joule can be used to express energy in all. I can take a chunk of matter, and I can say, in this chunk of matter, what is its energy in joules? Okay, and then I can use that energy in joules and like convert it into energy in electron volts, or convert it into any other form of energy. I could say, if you converted this matter all into kinetic energy, what would its energy be, right? So the joule lets us kind of convert back and forth between different types of energy. It's sort of the fundamental unit of energy. How much is a joule? A joule of energy is enough energy to take a half-kilogram object, roughly a 1-pound object, and get it moving to a speed of about 16 kilometers per hour. It's not important necessarily exactly what that is. It's sort of a way to just tell you a joule means an amount of energy. Okay. So this next statement is so important. It is one of the most important statements in all of physics as it pertains to radiography, and as it pertains to all of physics, but it is the statement that, simply put, energy is conserved in any closed system. But let me read from here. As a conserved quantity, the total energy within any closed system remains constant. Okay? It cannot be created from nothing, nor be destroyed such that it disappears. Energy isn't created or destroyed. Energy changes forms. So when I dropped the coffee cup and it shattered and all those pieces went everywhere, every piece, if I added up the kinetic energy of all of those pieces of that coffee mug flying across the room, if I added up all that kinetic energy, that would equal the kinetic energy of the entire cup at the moment that it hit the ground. Okay, and that kinetic energy of the cup at the moment that it hit the ground is exactly equal to the amount of potential energy that I put into it to start with. Okay, and you can work this statement all the way back. The potential energy in the cup is exactly equal to the amount of energy that I used to pick the cup up. Okay, and you could keep walking it back and back and back, all the way to, the sun gave energy to the plants, the cow ate the plants, I ate the cow, I used the cow energy to pick up the cup because the cow gave me, energy. So you can walk that statement all the way back, but we don't need to do that. The point is, energy is conserved in a closed system, okay? But like, you get home tonight, you don't feel like your energy's conserved. right? You're gonna feel pretty worn out, right? You learned some things, you drove all the way here and drove all the way back, right? You're gonna be pretty tired when you go home, right? So to you, it doesn't feel like energy is conserved. Like I ate all this food today, I used it, I did some stuff, but now I'm worn out, I'm tired, right? I literally feel like I have less energy. I don't have the ability to do work, right? The important thing about you is that you are not a closed system. You are an open system. You have to eat food, you poop and you pee and you release heat to the world, right? You're an open system. You interact with the world, okay? But the universe is a closed system. So in the universe, there's nothing outside of the universe interacting with the universe. The universe is a closed system, and we can build closed systems in science and engineering. Well, anyways, the point is in a closed system, in a system where nothing is going to interact with what's happening inside of this whatever system we're talking about. It can be the whole universe, or it can be a light bulb. Okay, in a closed system, energy remains constant. However, um, energy is conserved, but there are other quantities in physics that are not conserved that can be multiplied or divided or made more or less by doing different things. For example, force. Force can be multiplied by using a lever. Okay, in CPR, we use that idea. We take our sternum, our breastbone, and it bends from up here, right at the top where our clavicle connects. If I push on your chest from right here, I can't compress your chest very much. But if I push on your chest from down here, I can use your sternum like a lever to squeeze your heart. Okay? I can increase the force that I'm applying by using leverage. So simple levers are force multipliers. Okay? Force is not a conserved quantity. Energy is a conserved quantity. So, good. Energy is conserved. Don't forget that, okay? Energy is conserved, but it doesn't stay in one form. In the example of the coffee cup falling, we talked about energy being converted multiple times, okay? I took my cup and I lifted it up. That means I increased the cup's potential energy by putting it in a position to fall, right? Moved it further from Earth. And then when I dropped the cup, I converted that potential, the energy of being in this position, and the cup began to fall, right? The cup lost potential because as it's falling, if you took a still frame photography as the cup is falling, it was here, now it's here, now it's here, and now it's here as it falls, right? And in each one of those still frames, it's at a lower position, okay? Each position, it's lost potential energy. But if you measure the velocity of the cup, the kinetic energy, which kinetic energy is calculated by measuring your mass and your velocity, but right now just velocity. If I measure the velocity of the cup as it falls, it's going to be speeding up. Okay, it will speed up in exact accordance to how much potential energy it has lost. Okay, but it didn't lose the potential, it was just converted into energy of movement, kinetic energy. So energy can not be created or destroyed, but it can change forms, such as the form that it takes in Einstein's equation, E equals mc squared. Now, again, as Dr. Tyson said, ignore the c squared. The c squared is just a constant. Constants are used in lots of different formulas. The constant is, as it implies, constant. It doesn't change, okay? But here's the important part about the constant, the speed of light. It's a big number, okay? So on this side of the formula, where mass is, you have c squared next to it. It's a big number. So to put this in different terms, and they even say it right here, it takes an extreme amount of energy to create a small amount of mass. Said in another way, in small amounts of matter, there are large amounts of energy. Okay? Matter is equivalent to energy, and if you convert a piece of matter purely into energy, it will equal a lot of energy. Okay? A lot of energy. Okay? But in diamond? How so? What are you thinking? So you have to put a lot of energy into the diamond, right? And if you break the diamond apart, then you release that energy, right? So yeah, it has the energy in it. But even in a single proton, the diamond, so diamond is a carbon lattice, right? Just carbon in a special crystal form, right? But the energy in the protons, right? If you converted all the energy in those protons to from their state of being a piece of matter into pure energy, you'd get something like billions of volts, like 900 and something billions of volts of energy out of that proton, a single proton, right? The important thing is though, matter doesn't in normal circumstances convert from matter into energy. Okay, it does in radioactivity, and it does when we do things like make nuclear weapons, fission and fusion weapons. The sun takes, the reason why the sun shines is because when it takes hydrogen protons and runs them into each other, the energy contained in two hydrogen atoms, when you fuse them into helium, helium has less energy than hydrogen. So the energy from the two hydrogen atoms is greater than the energy of a helium atom. So that leftover energy, when hydrogen fuses into helium, that leaves the event as radiation. That's why the sun radiates energy at us. That's why the sun shines. Okay, because of E equals mc squared, the sun shines. Okay. All right. So energy and mass are equivalent, but not directly. Energy is not equal to mass. One piece of matter does not equate to one chunk of energy. It takes a lot of matter to make, it takes a lot of energy to make a little bit of matter, and it takes, and a little bit of matter can create a lot of energy. Okay, this is why we can make nuclear weapons. All right. So the rest energy of a particle is what we say its energy is, okay? So rest energy is if a particle is just chilling, sitting there, not speeding around, okay, which, by the way, under normal circumstances, atoms don't do that. Particles don't do that. Particles don't ever sit still in space. Particles are always in motion, so they have a rest energy, but they're never just sitting still, okay? However, though, if a particle is annihilated, converted into pure energy, then all of its mass gets converted into energy, and if it were an electron, its mass converted completely into energy would equate to about 510,000 volts. Your protons, there it is, 938 billion volts of energy. You can convert volts to joules. I won't do the conversion factor right now, but there is a way to convert volts to joules, so just don't worry about that. There would be an energy in joules. And then if you, yourself, about 4 times 10 to the 37 volts, that's 4 followed by 37 zeros, okay? So big old string of zeros, that many volts. To give you a feel for that, 10 to the 12 is a trillion. And every decimal point, every increase in the exponent is increasing the number 10 times. You go from 10 to the 12 to 10 to the 15, that number is now 1,000 times bigger. Okay, so each little increase in the exponent means a big increase in the number. Okay, 10 to the 37 is a huge number. All right, I will give us a lunch break in just a moment here, because we're getting to where we need to keep talking, but also need to stop talking for a little while. All right, so we call things that convert energy into other forms, we call them transducers. Any device that can convert energy from one form into another. A good example is in ultrasound. Those guys in here scanning right now, they're using sound waves, okay? And so what they have is they have something called a transducer. They hold it in their hand, and this transducer, inside of it has a crystal. The crystal is called a piezoelectric crystal. And what it does is you send electricity. So piezoelectric crystals are pieces of matter that when you run an electric current through them, they vibrate, okay, and create sound waves, okay? And when sound waves hit them, So the opposite happening. When sound waves hit them, they create an electric current. Okay, so you have a thing, you send out a sound wave, that sound wave travels through the body, bounces off the body and back to the detector, and then when the sound waves hit the transducer, it vibrates that piezoelectric crystal, creates some current, goes back to the computer. The computer turns that into an image that you see on the screen. Okay, that's transducer. A light bulb is a transducer. What is a light bulb converting? What type of energy into what type of energy? Electricity into?
Light.
Say it in terms we like to use. You took electricity and you converted it into light, but light is electromagnetic energy. So you converted electricity. Basically, you converted electrical energy into electromagnetic radiation. Okay. Yeah. So energy can change forms. Transducers are things that change the forms of energy. So there's chemical energy, the energy locked up in chemicals. For example, what's a good example here? Well, water. There's energy in water, right? Hydrogen and oxygen are reactive in the right circumstances, but when they're locked up in as water molecules, they're harmless. They're just water. Okay, chemical energy. Electrical energy deals with the flow of electrons. We talked a little bit about electrons, and Tyson did too, but the electrical energy deals with the flow of electrons. Thermal energy, and this is a little bit misleading, because thermal energy is also electromagnetic energy. Thermal energy is just infrared radiation, which is a type of electromagnetic energy. So we could almost just delete thermal. Nuclear energy, the energy locked up in those protons stuck together, okay? And those neutrons locked in the nucleus of an atom. And when those things break, that releases energy. That's radioactivity. And then there's mechanical energy. Now that's one we're going to talk a lot about. So mechanical energy can be divided into kinetic, the energy of motion, and potential, the energy of position. And as you just learned in the coffee cup analogy, these things convert, right? The law of conservation says the sum of an object's kinetic and potential energy must always remain constant. Okay? If I start off with an amount of potential energy, on the other side of the interaction or the equation, I can't have less kinetic energy than I started off with in potential energy. It had to go somewhere. Okay? So the energy is there. The energy is constant from beginning to end. The pull of an atom's nucleus on the orbiting electrons, similar to the pull of gravity on us or my coffee cup. Okay, an electron's position in relationship to the nucleus of an atom is like your position in relationship to the ground. Okay, if I stand on this table, I have a greater chance of falling off of the table than if I stood on the ground. Right? If I fall standing on the ground, I might get a little bump and a bruise. If I go get up on top of a ladder and fall, I'm going to get a much bigger bump and bruise. I'm probably going to get some broken bones. I might even get worse, right? Because of my position on top of the ladder, I had more potential energy to convert into kinetic energy, which would put more energy into me when I hit the ground. Remember, the ground hits back. So it's like that in atoms. The potential energy of orbiting electrons is represented by how far the electron is from the center of the atom. The ones that are very close to the center of the atom have very low potential energy. And so if they go from their position to even closer to the center of the atom, they don't have a lot of energy to lose, okay? But an electron from an outer orbiting shell, the outer shell of the atom, if it loses potential energy, if it falls down into a lower position, and there's reasons why that would happen, but if it falls down into a lower position, goes from high to low position in the atom, it's like me falling from the table to the floor. I'm going to convert my potential, my energy of position, into kinetic energy if I fall from the table to the floor. It just so happens that when electrons fall from high positions of potential energy, they don't convert their energy into kinetic energy. They convert their energy into electromagnetic waves. They convert their energy into photons. Yeah.
So when that's released, does that go in a specific direction? Does it go away from the center or towards the
Away,
center?
away. Importantly, though, photons have no electric charge, so they're not attracted or repelled from anything. Just the direction they get emitted in is the direction that they travel. So this is a good example. When an electron, as I said, when an electron out here falls, because okay, so atoms would like it if all of the electrons were at the lowest position possible, right? It's kind of like being here on Earth, right? Earth would really like it if we were all just right here attached to the ground, right? It takes work, it takes energy to get me up onto the table or climb up that ladder, right? Earth doesn't want me up on the ladder, Earth wants me to be attached to it, right? So in atoms, electrons are pulled to the lowest position that they can be, okay? If an atom's electron shells, because they're arranged in these shells, if its inner shell is full and then one of the electrons is removed, that's an open space where another electron from higher up could fall into, and the atom wants to pull that electron down, okay? So you have an open space here because of things that we'll talk about. There's an open space here. If this electron drops to a lower position, it loses potential energy. The law of conservation of energy says, however much potential energy it lost from going from here to here needs to be converted into some form of energy. Electrons convert their energy of position into electromagnetic potential energy, or a photon of light, okay? And depending on how much potential energy was lost from here to here, that will increase or decrease the energy of the photon released. Okay?
So,
Yeah.
so if the space that's left open,
Mm-hmm.
then is that, if it's next to another, another element, would it pull from that element to fill that space?
If you're asking if this space were,
If the strength of it is greater than the other element.
so it wouldn't pull from another element nearby. It would pull from a shell of that atom, an electron shell in that same atom, that's an electron shell above the one that we're currently at. Now, what I think you're getting at is if this happened in the outer shell.
Right.
If this were in the outer shell,
Yeah.
which if you're paying attention, right, I'm assuming you are, this, what they're going to call the L shell electron, if this comes down to here and does that whole interaction, right, that's going to then, what they're not showing you here, is that's going to then leave an open space here. Right. So now we have an open space. At that point, now this outer shell is called the valence shell, and at that point, another atom nearby would donate an electron to,
And that would leave them empty.
and that would leave them potentially empty, and they'd have to get another one. So there's this whole chain of
So this is a chain reaction.
this is why molecules will change shape, and why it's not good for radiation to hit living things, because it changes the position of the electrons, which changes the interaction between this atom and this atom, right? And these atoms change shape, changing the shape of molecules, changing the shape of things like DNA, breaking DNA strands, and a whole bunch of bad things.
So then that's how we end up with cancer.
That's how we end up with things like cancer. Yeah.
Oh,
Yeah.
okay.
Yeah, that's it.
Ah, I understand. That's not at all.
But everything's made of atoms.
Okay.
Atoms make molecules. Molecules make things like DNA. If you change the position of an electron in an atom, you might cause that atom to interact differently with an atom nearby, and that may change the shape of a molecule. You change the shape of a molecule, and if it's in the right spot, like in a DNA strand, then you change the shape of the DNA strand. If you do it in the right way or enough times, then you develop mutations in the DNA, and then you make potentially cancerous changes in the DNA. So it's this whole kind of chain of events that goes up and up and up to like the level of a body having cancer, but starts with a single or many atoms having this kind of interaction. Okay. Now, importantly, atoms do this all the time. Okay. Electrons freely move between atoms all the time. Atoms are always receiving energy or losing energy, so it's not like this happens and cancer happens. It's that this is happening all the time. Okay, so an electron can emit a photon of light when it loses position. Okay, it can emit photons when it loses position. The exact opposite can happen too. An electron in a low position can absorb an incoming photon, and that would raise its position. Okay? So an X-ray photon or a photon of light can come in, strike an electron. The energy from that photon gets deposited into the orbiting electron in whatever position it's in, and it can, if the photon has enough energy, raise the electron to a higher energy state. Okay? This is the principle behind all glow-in-the-dark things. It's that they receive light because you held them under a light bulb, right? All of their electrons raise up to higher energy levels, and then you take it away from the light source, and all those electrons can't maintain those high levels of energy, so they all jump back down into their atoms, okay, into their lower energy states. And you just learned that when an electron jumps from a high energy state to a low energy state, it emits light, okay? And so the glow-in-the-dark thing, all of its electrons begin to jump back into their low energy states, and light starts coming out, and you see that green glow-in-the-dark thing happening, okay? Does the green glow-in-the-dark thing do that forever? No. Eventually it dims, and goes to nothing, right? And you have to do what to get it to shine again? Hold it under light again. Deposit more energy into it. Put more work into the material, okay? So this is the key. The key is electrons absorb or emit photons of light to gain or lose potential. Okay, that's the story. Okay, all electromagnetic phenomenon, all types of light, X-rays, radio waves, come from electrons changing their position in an atom and releasing the extra energy as a photon of light. Okay, that's it. That's these two slides tell you everything you need to know with conceptually. Okay, now physically what's happening is a little bit different, and calculationally the numbers we're going to get from it, that's a different story, but the concept, it's there. We need to take a break. Okay, so let's do that. Let's take a lunch break. Yep.